Uh, uh, Hi everyone, I'm Saksham and thanks for having me. And today I'll be presenting our work on object removal in videos. And This work was done when I did my internship at Adobe Research India, and this was recently presented at this CVPR. Uh, a little bit about me. I'm a final year PhD student. So if you're looking for interns or full timers, please I'll be happy if you can reach out. And My advisor is Yapan Tian. A fun fact, like my advisor is actually Dr. Jason Corso, who is the founder of Voxel. Loop and My research interest is around computer vision and multimodal audio. And I also like to play guitar and tennis. In this talk, we'll be going over the object removal in videos, and I'll start with motivation and problem, and then our proposed approach. Then I'll touch upon like quantifying the metrics on like removal of objects in videos, and then benchmarking it and some examples. So I'll start with an example. Like when we come back from a trip and we revisit our videos and we are planning to post it somewhere, we observe that there are some people or distractions in our videos which come in our way of like the serene, peaceful setting moments that we had and wish if they were removed, we could have a yeah, we could revisit our memories of the locations that we were in. And this is not only this problem of object removal in videos is not restricted to this personal case, but also it can be extended to privacy, yeah, preserving privacy, and also removing like crew members or like microphones in videos or in movies in editing and other widespread applications. Traditional approach towards this is to use editing softwares, which is tiresome and it requires some uh, uh, unconventional expertise. And with and When the new models, large-scale video generation models have come up, so researchers have tried to tackle this problem by like partially or fully training these models. And But there are some limitations, like what if there are new applications come up tomorrow, then we will have to actually train it again. And With time, the models have keep on improving, so we will have to train them again. And Still, there are bigger issues than like more applications or more models, which is like not everyone has access to the compute or the money or the time, and also collecting data itself is a having like real world pairs of video editing or removal is difficult, and hence we try to answer a question like can we do it in a training free manner. So since like this video generation models have been trained on like enormous data, we assume that they have understanding of the world. So our hypothesis of this project was that they have the understanding of the world, and we just have to bring that up explicitly and use them to remove objects in the video. Uh, More formally, like given our input video, we want to remove the object and any associated effect. And while doing that, we want to keep the weights of the model to be frozen and come up with an algorithm such that we can do that. And Training free approaches used for image or video editing, there's a very popular paradigm of inversion and denoising. And our approach is also based on that. So in inversion and denoising, uh, we start with the input video and its caption, and then we go back, we try to map it back to the the noise, and then from noise we try to map it back to the video space distribution and with our desired text or a caption. So here, like we want to remove the dog. So the target caption is removing or like an empty water body. And also, while since we want to reconstruct the video itself, we also want to copy some intermediate attention values of the model. And but though this approach seems to work in like simple editing tasks or stylization for image or videos, we found that this simple inversion or denoising uh, actually cannot remove the object and essentially gives us a like identical video itself. So so in this project, we actually found some technical challenges and we systematically tried to remove them. And we think like an effective object removal in videos should remove all the remnants. There should be no remnants of the video or objects in it. And when we are removing an object, we do not want, we also want to remove the object, but also its like shadow or reflections in it. We also want to preserve the background. We do not want to have any artifacts in it. And when we remove an object, we also want to in paint it like homogeneously. Like here, there's a cemented platform that has come up, which seems slightly unnatural. So we want to tackle that. So we'll systematically start and about the remnants. We observe that these remnants occur because when we try to map the video itself towards the noise, then the noise itself has some structural or semantic information which is related with the video itself, and that actually pushes towards slightly creating the objects or leaving any remnants in it. So we modify this approach and in the noise itself, we try to, using the pixel mask, we try to reinitialize this object region with a random Gaussian. Um, and so we observe that doing so, we can remove any remnants of the object. And yeah, this was previously, and this is after our reinitialization of noise. And next, to preserve the background, so yeah, uh, while doing inversion and then denoising, we store some intermediate values and try to copy it, and we want to keep it only copy the attention values corresponding to the background region, and we observe that even like simply determining the background and using that uh, does not help, and so we went a little deeper in it. And when we are denoising, like when we are in the video distribution, going back to the noise distribution, and at different time steps, we try to observe like how is the mask response, which is essentially like given this object, what are the patches in the video which are like closely related to it. So the redder region means like it's highly related to this object, and we observe that this actually spills or bleeds, and as we go towards the noise, the object presence is actually increasing, and this happens because there's a lot of self-attention throughout different layers and time steps that have happened. And previously, using a fixed mask, which would actually not cover all the related tokens to it. And as we can see, like there are highly activated regions which are closely related to the object mask. If we copy the values corresponding to that in our approach, then this would actually hinder removing the object. And hence we propose like time, sorry, time adaptive masking, which is essentially we expand our mask more semantically or based on the object presence score. And this is more implementation wise. This can be actually done online approach itself, and we can determine this while we are inverting, and we can use that while we are denoising. And we can observe that doing so actually removes any artifacts or and better preserves the background. And now moving on to like associated effects. When we remove an object, we do not want like their shadows or reflections to exist, and hence we came up with an offline approach. We use the intermediate values of the model itself. We use a MMDIT based model, which is we use Hunyan. So in MMDIT, there are layers in which like the text and the visual patches share same embedding space, and we utilize that. So, given the object and its associated mask, we try to find like what are the regions that it is highly related to, and then we threshold that. But due to the text and visual having weaker correlation, we find that we still have like internal holes in it, or and it's not compact as a mask. And so we do another refinement of it. We try to find the visual patches which are highly correlated to it, and then we threshold it. So you can observe like a duck and its reflection in the water, both are now covered by this patch level mask. And we find that this approach generalized towards like reflections, shadows, and mirror reflections. And so, for example, the cat, we can find both cat and its reflection. And so we can modify our approach, like given the video and pixel level mask, we can offline determine this object and associated mask, and we can update our foreground region, or actually augment it both at reinitialization and while copying it. And we observe that when we use like associated mask, we can actually remove the object and its associated effect. Next, about homogeneous in painting, we observe that when we when we remove a larger objects, uh, then the model tries to replace it with another object rather than something borrowing more from the background itself. So uh, to overcome that, what we do is like we actually manipulate the attention. So for the object region, we make it to weigh more towards the background so that it looks more. It try to borrow more or attend more towards the background so that it can in paint it. And for background, we actually make it to attend less towards the object itself so that the background is disentangled from the object and can retain itself more. And more formally or implementation wise, during inversion during inversion and for denoising, we implement this like throughout most of the initial time steps. And we observe that implementing or using this attention scaling, uh, we can we can infill the region or in paint the foreground region with a more natural in a more natural way. And yeah, just a recap of our entire pipeline. We start with a input video and a pixel mask. We offline determine the object and its associated mask, and we invert, go towards the noise. While inversion, we determine the um, the foreground region, the adaptive masking, and we also do attention scaling. Then we reinitialize the foreground region with random noise so that there are no remnants, and then we denoise it back. And While denoising, we do attention scaling. Background looks less at foreground. Foreground looks more at background, and also we reconstruct or copy values for background. Uh, and We also use like text prompt, which drives it towards removing the object, and using all of them results in removal of the object and its associated effects. And here are some examples which in which we show our approach in like several different associated effects. Like the green are the mask, pixel mask, which is provided by the user, or you can determine it using SAM 2, SAM 3. And yeah, for reflections, it can remove the object and its associated actually reflection, which is disconnected. It can remove an object and its shadow. It can remove the cat and its mirror reflection. We can also remove like translucent objects. And yeah, uh, so next, moving on to how to quantify this object removal in videos. We found like uh, uh, previous approaches rely on human study or user study to determine like how is the removal quality, and this is and also there are no reference-free metrics to quantify object removal, and so this makes it difficult for to scaling up a good object removal, maybe making a benchmark or quantifying it or maybe standardizing it. So, and we explicitly tried to experiment with this. And so we took three scenarios, given an input video and three different settings in which the object is not at all removed, partially or fully removed. And we tried to get like the usual metrics which are used for object removal, like background PSNR or visual quality, then we find that this is not actually able to distinguish between these three settings quite well. And so we come up with a new metric which is based on token similarity. We use the patch level embeddings of like using the Dino V3 model, and given the input video and a predicted video, we hypothesize or like a good object removal uh, is when your object removed region is actually far from the original object region, and it's since it's a video, it should be temporarily consistent through frames, and uh, s- it should be well in painted, so it should be close towards it the boundary, its neighboring background regions, and uh, this is more formulated way. Like we actually calculate it over all the frames, and then we calculate it for all the object patches that we have, and then we reward temporal and foreground background consistency while we penalize it for being close towards the ground truth object. And we observe that this is actually able to distinguish uh, in these three different settings. So uh, you can we can find that it highly penalizes when the object is fully reconstructed, and it highly rewards when the object is fully removed. So yeah, and next we found that there is no real world benchmark for object removal uh, along with associated effects. So we collected videos from Pixel, and we created a small benchmark, evaluation benchmark for around 60 videos, which covers a lot of scenarios like reflections, mirror reflections, translucence, and shadows. And there are also different scenarios like object and its disconnected uh, effect object, and there could be like different multiple associations like its reflection and shadows. And yeah, uh, so and then we here is a quantitative comparison over like two different benchmarks that we have. We compare it with training free and training based approaches. We also have some reference, and we go over several different metrics like how is the object removal, how is the background preservation, and how well does it align with the given text. And we observe that our approach is able to better remove the object and better align with uh, the text. And we do find it slightly lagging behind in like of the background reconstruction. Uh, However, we found like background reconstruction is not exactly related to object removal, but we assume that with time, this should, with time, like when better video generation models come up, their VA improve, this should also improve along with our algorithm. And before concluding, I would just like to point towards our website that we have. So there we have like a lot of examples in it, and we have a lot of examples here. You can go around, have a look. You can also go around and look at the benchmark. We have released the evaluation code and how we created the mask for them. However, we were not able to release the code for the algorithm because it's under patent review. And but yeah, you can have a look at like several different examples. Like if this is the given mask and if you remove it, then like you can actually remove it pretty well, and several different scenarios. Uh, and uh, yeah, translucent, maybe fast moving objects. It's a pretty robust approach. We also tried it at a different model. It seems to work pretty well in it. So yeah, I'll again go back to our slides. Uh, yeah, so overall, we propose a training-free approach, and we try to explicitly bring out the video understanding knowledge that the large T2V models have. And we think that this is not limited to removing the object, but it can be extended to like several different applications. And our several insights that we got from this project can be generalized to different editing tasks or addition or any other task. And we also propose to remove the object and also its associated effects. And we also pointed out towards like lack of quantifiable metric, and we try to tackle it with uh, token level uh, token level metrics. And we also pointed out like there is no real benchmark which is specifically for objects and its associated effects. So yeah, uh, I I hope I'm well within time, and I'll be happy to take any uh, questions if you have.